And so next, I will be going over the problems for math levels 3 and 4. So, yeah. So first, level 3. So we're given that W and Z are complex numbers such that the magnitude of W plus Z is 1, and the magnitude of W squared plus Z squared is 14. And so we're trying to minimize the value of the magnitude of W cubed plus Z cubed. And this is just defining what magnitude is. And if you don't know, the magnitude of an imaginary number of the form a plus bi is the square root of a squared plus b squared. In other words, it's the distance to the origin in the complex plane. So yeah. So now, first what we want to do is basically simplify w cubed plus z cubed. So this is equal to the magnitude of w cubed plus z cubed. So this is equal to the magnitude of, so what we do first is just factor w cubed plus z cubed into w plus z times w squared minus wz plus z squared. And so the magnitudes are multiplicative. And so that means that this is equal to the magnitude of w plus z times the magnitude of w squared minus wz plus z squared. And so from this part, we see that this is just equal to 1. And so this is just equal to this. And so finally, we can simplify this furthermore into 3/2 of w squared plus c squared minus 1/2 of w plus c squared. And so the reason we do this split is just because we're given everything in terms of w plus z and w squared plus z squared. So instead of keeping it in this form, it would be better to use w plus z squared and w squared plus z squared. So yeah. And so next, what we do here is that we next apply the triangle inequality. Okay. And so what the triangle inequality says in terms of magnitudes for complex numbers is just the fact, it's just the fact that the magnitude of a plus b is at most the magnitude of a plus the magnitude of b. And the equal sign here is, okay, so yeah. So the equal sign here is only holds true when a and b follow the same direction, if you can understand. So what I mean by follow the same direction is basically like, if this is a complex plane and this is A, then this is B. Well, B can be any point on the line. So yeah, any point on this line. On the positive side of this line. Yeah, like that. And yeah. So that gives us that, this gives us that 3/2 of w squared plus z squared minus 1/2 of w plus z squared, and then plus another 1/2 times w plus z squared is greater than or equal to okay. Sorry, so this is greater than or equal to 3/2 of sorry, not greater than equal to, less than equal to. Why did I write that? Okay, 3/2 of w squared plus z squared minus 1/2 of w plus z squared, and then plus the magnitude of 1/2 of w plus z squared. Yeah, so like that. I'll do a bit more. Oh, whatever. This will just have to be. Okay, yeah. Sorry. So I'll just rewrite this. The triangle inequality. Well, in terms of magnitude for complex numbers, is just a plus b. The magnitude of a plus b is at most the magnitude of a plus the magnitude of b. And where equality holds for how I described it earlier. Yeah. And so now that we know this, we can just plug it back into this. So we have that. So from here we have that the magnitude of w cubed plus z cubed is equal to the magnitude of 3/2 times w squared plus z squared minus 1/2 of w plus z squared. And this is greater than or equal to 3/2 of the magnitude of w squared plus z squared minus 1/2 the magnitude of w plus z squared. And so if we remember from our original statement, here the magnitude we're given the magnitude of w plus z and w squared plus z squared. So this goes to 1 and this goes to 14. So this is equal to 21 minus 1/2 or 41 divided by 2. And so the minimum value that we found is just 41 over 2. And if we want to prove this, then the only inequality here is this one. Better if I use it. The only inequality here is the one I underlined. And so if you remember the equality case, that just means that the w plus z and w squared plus z squared are in the same direction. So one possible special case of this would be if w plus z is equal to 1 and w squared plus z squared is equal to 14. And if we find any wz that work for this case, which we should, because we can use imaginary numbers, complex numbers, then we can see that the magnitude of w cubed plus z cubed is simply just 41 divided by 2. So yeah, the answer is 41 divided by 2. All right. So are there any questions? Okay. Well, if there are no questions, I'll move on to the next question. So let a, b, and c be positive real numbers such that a squared plus b squared plus c squared plus a plus b plus c squared is at most 4. So prove that ab plus 1 over a plus b squared plus bc plus 1 over b plus c squared plus ca plus 1 over c plus a squared is at most. Yeah. So the first thing we can do is look at just this. So we have that a squared plus b squared plus c squared plus a plus b plus c squared. A plus b plus c squared is equal to 2a squared plus 2b squared plus 2c squared plus 2ab plus 2bc plus 2ca, which is just equal to exactly a plus b squared plus b plus c squared plus c plus a squared. Okay. And so, just for the sake of simplifying this, we can make some substitutions. Namely, and just so they make sense, we will use Greek letters corresponding to which of the three letters is missing in the pairs. So alpha is equal to b plus c, beta will be equal to c plus a, and gamma will be equal to a plus b. And so if we want to, so I'll just write this out. So alpha equals b plus c, beta equals c plus a, and gamma equals a plus c. So if we want to calculate a, then what we can do in terms of alpha, beta, and gamma, then what we have to do is b plus c, and that would give 2a plus b plus c, and then we subtract out a and divide by 2. So then we have that a is equal to beta plus gamma minus alpha divided by 2. And similarly, we also have that. And so if we do this for b and c, then we see that b is equal to alpha plus gamma minus beta over 2, and c is equal to alpha plus beta minus gamma divided by 2. Okay. And so the usefulness of the substitution is that we can now just directly write alpha squared plus beta squared plus gamma squared is at most 4. Okay. And so now we look at this left-hand side. So the left-hand side is ab plus 1 over a plus b squared plus bc plus 1 over b plus c squared plus ca plus 1 over c plus a squared. And this is at least 3. Okay. So yeah. So if you can easily see really that this denominator, oh, it's not close. That this denominator is gamma squared. And so we look at the numerator next. So AB plus 1. So the only way we can get a term of AB without forming any other terms of pairs, without forming any other pairs of two variables being multiplied together is with gamma squared. So then after that, we need to subtract. So basically, AB is equal to gamma squared minus a squared minus b squared divided by 2. So if we further do this, If we further calculate this, then this is just equal to then a squared plus b squared. Sorry. Then a squared plus b squared can then be sorry. A squared plus b squared can then be formed from a squared plus b squared can be formed from alpha plus beta squared. So gamma squared minus alpha plus beta squared. Okay. Oh, sorry, not alpha plus beta. Alpha minus beta. Okay. And so, yeah. And so, at the same time, this thing needs another, sorry, this thing adds another plus 2ab. Oh, sorry, no. I didn't write that. I meant minus 2ab. So this means that 2ab is equal to gamma squared minus alpha minus not plus, minus beta squared divided by 2. And so what that means is that AB is equal to gamma squared minus alpha minus beta squared divided by 4. So this term is equal to gamma squared minus alpha minus beta squared over 4 plus 1 over gamma squared, which is equal to gamma squared minus alpha minus beta squared plus 4 divided by 4 gamma squared. And so if we repeat this, then we see that BC plus 1 is simply just alpha squared minus beta minus gamma squared plus 4 divided by 4 times alpha squared. And this finally is equal to beta squared minus gamma minus alpha squared plus 4 divided by 4 beta squared. So here we can see that this is equal to gamma squared minus alpha plus, not plus, alpha minus beta squared plus 4 over 4 gamma squared plus alpha squared minus beta minus gamma squared plus 4 over 4 alpha squared plus beta squared minus beta squared minus gamma minus alpha squared plus 4 over 4 beta squared is, and so yeah, so this simplifies it. And so next, we already know that alpha squared plus beta squared plus gamma squared is almost 4. So then this is at least equal to gamma squared minus minus alpha squared minus beta squared plus 2 alpha beta plus alpha squared plus beta squared plus gamma squared over 4 gamma squared. And so we can simplify this by canceling out stuff. So here, alpha squared, alpha squared, beta squared. So this is equal to 2 gamma squared. So, and then there's another factor of 2 that we can simplify out. So that gets this down to gamma squared plus alpha beta over 2 gamma squared. Okay. And so the same will obviously hold true for the other 3 values. So plus beta squared plus gamma alpha over 2 beta squared plus gamma squared plus alpha beta over 2 gamma. That should be alpha. Alpha squared plus beta gamma over 2 alpha squared. And so this is just equal to 3 halves plus alpha beta over 2 gamma squared plus beta gamma over 2 alpha squared plus gamma alpha over 2 beta squared. And so next, what we do is we can look at this. So alpha beta over 2 gamma squared plus beta gamma over 2 alpha squared plus gamma alpha over 2 beta squared is at least equal to 3 times the cube roots of the product of these numbers, which would be alpha beta over 2 gamma squared times beta gamma over 2 alpha squared times gamma alpha over 2 beta squared, which is equal to 3 times the cube root of 1/8, or 3 halves. And this holds true just purely through AMGM inequality. And if you don't know what that is, it's simply just so this is the AMGM for 3 variables. So for 3 variables, it states that a plus b plus c over 3 is at most the cube root of ABC. So continuing on from here, this would then be at most 3 halves plus 3 halves, which is equal to 3. And so if you remember, the original problem simply wanted us to show that this was true. This was at least 3. And so we've just shown that it's at least 3 halves plus 3 halves, or 3 down here. Down here. So that proves that the inequality is true. And so, does anyone have any questions? Okay, well, I guess if not, then I guess that's it for today. And so thank you for coming, and I hope you have a nice weekend.